So we are going to continue this chapter, still chapter number 1, and the numerical method used in modeling of FN structure. So this is the part 3. The third time we are doing the same topic, numerical method. Okay. So this time we are going to talk about equilibrium and compatibility condition in numerical analysis. So when we use the finite element method to solve geotechnical problem, it involving static or dynamic condition. One, we must satisfy the force equilibrium equations or equation of motion, just movement, respectively. Okay. So on the other hand, for any general system, the equations of motions must be satisfied under transient condition. Okay. In addition, the volumetric compatibility between pore water and the soil skeleton must also be secured, must be guaranteed as well. We have to guarantee that also. Okay. Therefore, the equation of equilibrium or equation of motion can be combined with those of volumetric compatibility between pore water and soil skeleton. For each element, we need to satisfy these equations. Okay. As an example, in the case of axisymmetric problem, do you remember the axisymmetric problem in this case? Okay. When we have the direction of R, Z here, and theta, the angle. In this case, for example, the resulting equation can be expressed for any given point in the direction of R, the radial direction. Okay. So it can be something like this. So it a quite long equation, but each U here is displacement of a point in this direction of the R. Okay. So displacement, and here this one is the average volumetric strain, this epsilon V in the element, and this K is here, K. This coefficient is hydraulic conductivity, or if you want, the permeability, which is assumed to be same in all directions. Okay, isotropic condition. P is the pore water pressure. Okay, so we have P here, the pore water pressure, and sigma M, this one, is the average normal stress, the mean normal stress, which is the average between the average of stress following the R direction, Z direction, and also this theta. Okay, just plus and divide by 3. And N, can see N here. N is the porosity of the soil skeleton. If you want, it is like taking void ratio divided by 1 plus void ratio. And Ks, this Ks here and here, compressibility of the solid grain. So everything, the last one here, compressibility of water. As you can see, this equation is combining almost everything about the soil. Okay, displacement, volumetric strain, hydraulic conductivity or permeability, pore water pressure, mean normal stress, porosity, compressibility of the soil and compressibility of water. And also in the other direction, similarly, we can write also. It means in the direction of Z and theta. Okay. Then using the standard, this Galerkin method, the above equation for a single point can be generalized for the total isoparametric finite element, because the previous equation was only for one point. Okay. So we can generalize it by using integration, achieve V volumetric integration here. This is, if you can see this, as you can see, this is the previous equation, this one only. Let me go back to show you this one. So this is for just one given point, okay? 1 point. This equation is for 1 point only. So we can integrate, summarize to obtain for a total volume for a given volume, okay? Integration. And it should be 0 because we should satisfy equilibrium, okay? Then n here is this matrix for the NE are defined. I think in the previously we have defined this, and these are here. Do you remember the shape functions? Shape function, we have discussed about this previously. I'm not sure if it was in the previous video or the video before that one, but we have discussed this shape function. So these are the n we have here. Okay, and the n value. This matrix is here. And the V is the volume of the finite element. For example, here we have several type. So as you can see, you have volume. For example, for each point, we have this equation, and we make integration to obtain for all the volume. Okay. We are still here, axisymmetric condition. Okay. So for R, and we can do it for all the three directions. Let me keep this equation here. So finally, by applying the standard FEA procedure, that means applying using the equation we have been talking about so far, from equation 1.33 to 1.43. Okay, using all these equations and summing up in this equation 45, sorry, over a certain number of element, m number of element, covering the entire domain, the total model that is modeled, the following stiffness relationship can be derived. So we can get this stiffness relationship. Summarizing everything from the beginning until this equation, we can obtain for n m number, means you can see here n going for 1 to m. M is the number of elements. If in your model you have 1,000 elements or 3,000 elements, it depends the number of elements you have. Okay, we can summarize all of them like in this equation, and it will be 0. Okay, so Vn, that one is Bn. From here to here, Vn is volume of the nth finite element. Okay, the element number n, the volume. We integrate volume. Okay, And Bn here is the boundary of the nth finite element. T now, T, you can see T here, I think, is traction force, means force per unit length along the boundary of the nth element. Let's keep this equation here. So this equation 47 is usually integrated within each element using the Gauss-Quadrature element. Using the Gauss-Quadrature method. So the integration point used 2 by 2 Gauss-Quadrature technique using this is indicated here. So this method is just like if you want to integrate this whole area to calculate the surface of this whole area, you can divide it in small areas. Okay, so this is using like 2 by 2, means four parts, dividing the total area in 4 small areas and calculating to estimate the integral. Okay, so this integration 1, 2, 3, 4, these coordinates are the global coordinate and these one are the local coordinate. Okay, and this point, the number of point, the Gauss integration point 4, because we have 2 by 2. Okay, so I think the information here we need to keep in mind is just we need to make like equilibrium to satisfy the motion. Okay, as you can see, this is very complex. That's why normally we use computers to calculate it. So after the integration operation and mathematical manipulation, this equation 47, this one, can be arranged in the form of similar to this equation 48. Okay, and corresponding stiffness matrix, the scale of the foundation, because we are dealing with foundation here, foundation structure can be obtained by comparison with this equation 48, this one. Okay, then when this stiffness matrix is of the foundation structure is available, we can use linear algebra solution, okay, to solve the unknown deflection and force. This is the force, this is the deflection, displacement, this is force, okay? Like reactions with the unknown boundary condition. I think that's all for this video. Maybe a little bit complicated, complex, but you don't have to worry because this is the job of the program. However, you need to understand that this is what the softwares are using to solve geotechnical problem, this kind of equations. Okay. Okay, thank you very much, and we stop here. See you soon.